All right, welcome back, everybody. Today is what, October 17th? I have played so much Hot Wheels over the last couple days because my kid is back, and that's super awesome. Uh, Showed him a video game. Didn't show him. He helped me pick a game on PS Plus, and it turns out Paw Patrol video game is also not very fun. Just throwing that out there. Not for me. All right, here we go. We're going to start Unit 2. Unit 2 is a big one. Because in Unit 2, all of a sudden we're making this change from talking about just motion and the basics of movement. Unit 2 will cover the next several chapters for us. Unit 2. And I'll just tell you how many chapters specifically because Liam asked this a second ago. Our first unit had how many chapters? 3. This one has 5. We get 5 chapters. Now, the cool thing, or maybe not the cool thing, there's only 3 sections for almost every chapter. Okay, looking at this, Unit 2, our entire focus is going to be this idea of energy. All right, now moving in with this, we have to address energy in a few different ways. So to kind of start rolling with it, we're going to jump in today, starting Chapter 4. And within Chapter 4, with the overarching theme of energy, we're going to be talking about 2 things that show up everywhere else, but I don't want us to confuse it. We're talking about work and energy. Okay, a lot of times in a physics class or physical science, which is where we happen to be, I would call this just like this class, physical science is a fine name, but I think of this class as being an introduction to 2 different main sciences. I think of this as an introduction to physics. That's a physical science, like you're dealing with physical objects. Do you know another one that's physical objects? That's not life in biology? Chemistry. I think of this class as like the introduction to physics and chemistry, which is kind of nice because the 2 ideas are actually really related when you get down to the small stuff. Okay, so within work and energy, my guess is you have seen a lot of this stuff before, but today we're going to start 4.1. And right off the bat, we're going to be talking about this first idea of work. So the name of this first section, 4.1, we have 2 main points to look at. We're going to be looking at work and machines. Okay, work and machines is our focus going on here. How many of you guys work? Anybody have a job in here? You have a job? Kind of? Like, whether it's a paid job or not, you're probably starting to work a little bit, right? What are you starting? Cool. Nice. You work at the restaurant. Where do you work, Vincent? Cool. Max? Hydraulics?
Yeah.
Cool.
I clean apartments and other.
Nice. Somebody back there had their hand raised.
I work with my dad at Salinas sometimes.
Cool. You go out on boats and fish? Cool. Awesome. All right. So, we all have an idea of work, obviously. Is that the type of work we're talking about in physics class, you think? Probably not. Now, when we're looking at this, our first main topic is we need to make sure that we have a good agreement on these things. Oftentimes, within the first section, there's a lot of vocab. We would benefit from more vocab quizzes and, like, review stuff. True or false? Like, you probably don't want more quizzes, obviously, but should we focus a little harder on the word stuff? Okay, I will make it a point to do that. Now, our first idea that we want to look at is this work, and we're going to give ourselves a nice definition, and we're going to go through the process of defining this idea of work. Klein, I'm super thirsty. Will you go get me a drink? Cool. So, in regular, like, everyday usage, if we were to talk about work, and like you guys just shared a little bit with me, how would you define work? Like the work that we were just talking about. Moving around, doing stuff. I'm cool with that. Do you guys agree? What's the end goal of work? So maybe it's to get something done. That's a nice one. But realistic is probably to get money. So, just have like as few words as possible. Tasks to get money. You guys agree with that? With like the simplest definition of like everyday work?
Side quest.
Yeah, side quest possibly. Awesome. Now, the cool thing is that we're not in everyday life. I mean, we are, but this class doesn't focus on just everyday regular life. We focus on the mechanics and how things work. So when we're in our physical science class, which I'm just going to say we're in physics right now, because we are doing physics, within the world of physics, work might be a little bit different. Now, Sonny, you do a lot of work, I think. And there's better places. Instead of just saying work like at the restaurant, for example, Sonny, what do you do often in your free time? Where do you go from here after school?
To the gym,
And what do you do at the gym?
work out.
You work out. And what does it mean to work out? You get on the treadmill and just run?
No, I don't do cardio.
Okay, so what do you do?
I either do shoulders, legs, biceps, or triceps.
So I assume you mean you lift
I lift, yeah.
weights to work on those muscle groups. Okay, now, anybody here who has ever lifted anything, which every single person has, right? Like, you can't live to this point without lifting something at some point. Do you have to apply force to it? And then do you have to make it move once you apply that force? Oh my gosh, we've been talking about forces and movement in Unit 1, right? We built up all this underlying language. So in our world, we're just going to say that work for us is applying force. So we'll say, and we'll make a better definition. Regards or relates, here we go, force and motion. Now, this is a nice idea because obviously if I want to push something, I have to push so hard in a certain direction, and to like really do it, I need to actually move it. Okay, I've just done work. I just worked out. Cool. Off the list today. We need, however, a much more formal definition of this. So right off the bat, here we go. We're going to define for ourselves work from a physics standpoint. Okay, super easy to define. We're going to say that work is simply the applied force. The applied force, which means something actually has to do this, right? The applied force. And then I need your input here because I have both words written and I don't remember which one I used last year. I'm going to say it has to happen over a distance. Does it make more sense to say the applied force through a distance or over a distance? So give me another word then. So like I'm going to apply a force and I'm going to move this thing. I have to keep pushing it or else it stops, right? So right now, but we have to, so check it out. I can apply a force to something, right? But I have to do it over some distance. So just now I walked a meter while I was applying a force. Through, over, other language it makes more sense. On some distance. I'll just put both and you pick which one, over or through. I think force, but then that makes me think of division, and I don't want the applied force over or through a distance. Okay. Now, if we were just to look at something, I want you guys to push without standing up. Push as hard as you can down on your desk. Okay. If I made you do this for the next 8 hours, do you think you'd be sore tomorrow? Would your muscles be sore? You say no? You don't think so? Push harder. I don't think that you could push like with all of your ability for hours without getting really sore, right? Or we'll try this. Grab your textbook or something heavy in front of you. Okay, straight out. Okay, not lift your arm. Even with an empty arm, it's going to be hard to do this after some time. Are you working out right now? So it's static though, there's no motion. Okay. With this definition in mind, keep them out as long as you can. We're just going to see how it goes. I wouldn't do it with your computer. Are you guys doing work right now?
Huh?
Are you doing work?
Yeah.
Are you sure?
Yeah.
Justify it.
Because your muscles have to like strengthen up.
Okay, so you're using your muscles. You're doing work in the working out sense. How about in physics? Are you doing work right now?
Yeah.
You say no, you say yeah. I don't care which side you pick. Keep them out as long as you can, or don't. It's up to you. Even with just an empty hand, you would struggle.
If I fail this, oh my god.
Okay, talk with your neighbors. I want you just to pick a side. Right now, as people are holding their books out, work is being done or work is not being done. I'm going to give you about a minute. All in all, no work was done by you guys just now. Because you have to apply this force, which we had done, but there was no distance being covered by it. Work requires you to move. Right now, all the work with quotations, because it's not real work, that Sonny just did, I'm doing more work right now than Sonny just did. Way more work. Why? Because I moved. Look how much I moved. Maybe a meter. How much did Sonny's book move when he held it out here?
Probably like an inch.
You didn't do any work. No work. We're just going to say you were perfectly still and didn't move it. There was no work done when Sonny held that book out. Now, going through this, it means that if you were to stand and push all day on a wall, there's no work being done because you're applying a force, but what's not happening? It's not moving. Now, all of a sudden, we're going to bring this back here, and I know that we wrote this down within the last couple weeks, but I just want to make sure that we have it. I'm going to put a tilde on that so that we can separate these. Beyond that, remind me, what's force? And this is a kind of vague question. One more time? Yeah, go for me too. All right. What's a force? A push or a pull? You guys good with that?
Yes.
What's the difference between a contact and a field force?
Field force, no contact.
So kind of. Give me an example of a contact force.
Gravity.
Ooh.
Wait, is it? Oh wait, contact force?
Yeah.
Oh my bad. Does that count?
Sure. Can you tell me what it was?
Friction or
Friction's a good one. Friction's a contact one. Literally just physically pushing something is a contact force. Riley, what's a field force?
gravity.
So that's an example of it. Gravity's one. Can you give me another example, Chelsea? I'm fighting this right now, but it's not touching. I mean, until you hear it click. It acts at a distance, right, without being in physical contact. Magnetism and gravity are the two easy ones. Okay, Klein, field forces don't have to touch objects, right? So we're just going to say this. Force, what's the letter that we use for this again? Ooh, careful. If I say what's the unit, N is okay, because N is for newtons. What's the label for force? F. Okay, if I put sub net, it's talking about the net force, which, what's net force?
Net force is a group of forces, right?
Like all the.
Love it. Ashley says the sum of all applied forces. Okay, now, force and work have something in common. If we push something and it goes some distance, does it probably have a direction with it? Like if I think about lifting versus pushing something, or this. Right now, I've pushed this in the positive or negative direction from your perspective.
Positive.
Probably positive. Now I'm applying a force just to undo this. It's moving in the what direction?
Negative.
Negative. Do you think that that might have something to do with work as well? Whether we have positive or negative work. Would it make sense then if we're talking about forces that this would also be a vector? Okay. So, as we look at this, we're just going to say force, and we've already defined this. We'll say force, just remember it's a push or a pull. A push or pull that may cause movement. Now, whether or not it causes movement varies depending on the object and the type of force that we're applying and all that stuff. If it does, I can spell movement instead of movement. Weird. If it does move when we push it, and we keep pushing it, we've done force over some distance, and all of a sudden we arrive at what? If we start pushing something, here I am, and it starts to move and I keep pushing it, I'm doing more than just applying force. I'm applying force over a distance, and we call that what? Work. Okay, as we look at this, let's just check it out. We're going to jump right into an equation. A push or pull that may, oh my gosh. What did you guys write down, just out of curiosity? Did you write down a push or pull that may movement?
That may cause.
May cause movement.
Okay. I definitely said the word cause, I just skipped it. Weird. Okay. If it causes movement last time, and I'm just going to sound like a broken record over and over today. If it causes movement, Jonah, we call that force that we've applied over some distance that caused movement. Whoa, whoa, whoa. Whoa, 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 whoa. Whoa, 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 whoa. Work, work, work. In the words of Rihanna, don't sing it. I take that back. We'll just get that song over our heads. Okay. Now, looking at it. Let's think about this. We're going to get a nice definition of this. And here's like the most important thing that we're going to see today. Have we ever talked about stars?
No.
Okay, so check this out. We're going to pause the video. Sorry about the awkward pause there. Here we go. If we are talking about work, and I'm being very intentional with my capitals just so you know. Work is equal to, what do we say was one of the fundamental parts of this? Force? Force. And then if I put this dot, I'm guessing we are all cool, but maybe not. We should verify. What does this dot mean? Times. Okay. And we'll use distance. Now, if you got to pick the rules, which most of the time you don't, but sometimes the things that you would pick are the same as what we'll actually pick, what letter would you use as a label, not a unit, a label for work? W, lowercase or capital?
Probably
Capital.
capital.
Capital W for work. Okay. Nothing to my mind, but this looks kind of like a lowercase w. It's actually a lowercase. This one up here, you don't need to write that. That looks like a lowercase w. It's a lowercase omega, and it's used for rotational velocity, which we'll get to. All right. So here we are. Work equals. Gosh, what's force again? F times distance, lowercase d. Okay. Work is force times distance. Here's my challenge for you guys for just a second. I don't think you know the actual way that we measure work, like the unit on it. You do not know it yet. But my challenge for you is I'm going to give you about 2 minutes. Do you know the units for force and distance typically? Okay. What's force? Oh, you're close. Okay. Here's my challenge for you. I want you to play the unit game here. We know I want you to write underneath or off to the side. Underneath makes more sense in my mind. I want you to write the SI units for force times the SI units for distance, and let me know what you get. Cool.
Wait, do you want us to use kilograms?
I want SI, so newtons aren't SI yet. If you want to say newtons times whatever you measure distance in, that's a good starting point. You might have to look back at what a newton is. I'm going to give you a second. I want you to tell me what the units on work with only SI units come out to be. Cool. So, real quickly, we're going to take, it's going to seem like a little side trip for just a moment. Anybody ever use a torque wrench?
Yeah.
Okay. Have you ever tightened something that's important and says don't over tighten it?
Yes.
It'll say tighten this to what?
So like something newtons, right?
It's not newtons, not on the tools that you guys use. Not a chance.
Oh, it's like something. Oh,
Have you guys ever seen foot pounds show up on a tool?
yes.
Okay. Foot pounds. Let's just think about that. That's not metric at all, but feet or a foot is a measure of what?
Like distance,
Distance, and then in non-SI units, what might a pound represent?
weight.
A weight or a force. So turns out you guys have seen things, maybe if you've ever seen a torque wrench where you can set stuff. Force is measured in newtons, right? Okay, so we'll all help you with this. Newtons. And distance is measured in what? Meters, M. Okay? Beyond this, what is a newton?
KGMS squared.
It's a kilogram meter per second squared. And now we're multiplying it by what? M. Okay, flex your algebra muscles. Your algebra muscles. How do you multiply these things? kg times m over s squared times m.
kg m squared divided by s squared.
Kilogram meters squared over second squared. Yay, nay. Is this pushing on the boundary of your math ability? Okay, this is weird, right? Like, this is a weird unit, and that's okay. I don't want you to erase yours, but I want mine to look a little bit nicer. Okay, when we're looking at this, there's 2 steps that I really worry about. We're going to say that this work, we're going to measure this, and I'll change that language, because when I say how do you measure work, you might try to think of scales and like rulers and things like that. Now what I'm looking at, the unit for work we just saw are going to come out to kilogram meter squared per second squared. That was correct. Okay, that's ugly. Don't love it. Instead, it'd be nice if we just had a single way to talk about it rather than that jumbled mess of like letters and stuff. So here we go. We measure work in the units known as joules. 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 Can't remember his first name. French physicist Dr. Joule was who came up with this. Okay, we measure them in joules. Where we have to be careful though, because it might show up a little bit differently. This one, if we don't go all the way to SI units, it was in what? Newtons. And this distance would be in what? Meters. Okay, a foot pound is a pretty common measurement in English, like American stuff. A Newton meter, turns out, is just the same thing. Force measured in newtons instead of pounds, and meters for distance rather than feet.
So it's like metric system like that?
This is metric. Yep, 100%. Now, the most important part of this is that we need to be able to pick out if a problem doesn't like make it super clear exactly what's happening. If you can get to newtons and it multiplies by meters, there's a better way to write it. Instead of newton meters, which we'll just say is Nm, you might call it joules instead. Okay, what's up? Okay. Okay, so real quickly, a newton meter is the same thing as a what?
Foot pound.
What? No, no, no.
A
A joule.
Oh, a jewel.
A joule. 1 newton applied over a 1 meter distance is a joule. Okay. Are we going to use foot pounds or newton meters in here, you think? Ooh, I like that answer too. We'll use newton meters and joules. Okay. Going through here. Let's do a problem. All right. So, practice is all I'm going to say. We'll do one problem. It doesn't look like we're going to have homework today. Sorry. Check it out. I'm going to pause it so that we don't have to record us watching this. But real quickly, I'm going to tell you the #1 secret to being successful in the world of money. All right. So check it out. We have one problem that this, realistically, it might be your homework. I might ask you to finish this. Here we go. I didn't mean to resume it. Okay. So nothing other than the fact that we've introduced work into this has really changed. What do we always start these problems with? Always. Known. Okay. Would you benefit from a picture?
No.
Okay.
Maybe.
I want you tonight to identify the known or the known information, the know. I want you to identify for me the find. And I'm going to give you a huge hookup here. I'm going to call this equation /scratch because I'm not going to call it work anymore. What's the equation we're going to use, do you think?
W equals FD.
W equals F.
Newton.
F
FD.
times D. All right. This problem's your homework. At 1:10 tomorrow, I'm going to check in your notes or the piece of paper that you bring if you don't have real notes. Finish it. Don't care if you're right or wrong. Either way, we'll learn something in the process. Later, Raiders.